Let's get it started. So the plan is we first have 4 presentations. After each presentation, we will ask questions. The time is 10 plus 5. If you go over 10, that means we have less than 5 minutes to ask you questions. Then if we don't get our questions answered, you know what happened. And after the 4 groups, we will take a short break. And after that break, we have 4 more groups. After everything's finished, we'll just go decide on your score. And we grade them, but we need to calculate that. Then from 4 to 5 will be just a winner announcement and the closing remarks. I don't think any of you really have to leave that early except Emily. But yeah. So let's get started. So the drawing comes from here. Does anyone question the randomness of this drawing? Okay, the first group will be, the first group.
Hi, I'm Bijeeta, and I'm going to present our work in collaboration with Travis, Sarah, and Alexander, and I will be talking about private outsourced translations. So imagine that a doctor has been posted in some remote village where nobody speaks the same language. In such a scenario, it becomes very difficult for the doctor to understand the patient and read patient's health history, and also for the patient to accurately translate and understand the prescriptions and the drug labels. In such a scenario, a translator will be really helpful, but most of the time, all the medical staffs are also won't know that language. So in this work, what we focus, and often these prescriptions consist of very small sentences and have a small vocabulary. And in this work, what we focus on is using translation for medical prescription using homomorphic encryption. And this is a pie in the sky because translation using homomorphic encryption is a very difficult task. But since we are focusing on very short sentences and a smaller vocabulary, we are hopeful to achieve this goal. So it was very difficult to get a data set for drug labels and drug instructions, and I think there is not any data set currently in that contains exactly what we needed. And it was also difficult to get data sets for medical because often you need more permissions to use medical data sets. So instead we used 2 short dummy data sets, one consisting of one called multi-30K data set that consisted of small German sentences that were translated into English, and a European medical data set that consisted of medical notes written in German and English. So some of the impractical alternative is one is that we can upload the medical documents to cloud service provider, but this requires trusting the service with medical documents. Another obvious solution is most of these cloud service providers, sometimes you can buy the software and download it into your machine, but this forces the client to buy these large dedicated softwares. And sometimes the cloud service provider don't want to give their proprietary model because then it becomes vulnerable to reverse engineering. Sometimes these language translation models that the cloud service providers provide a much smaller model that can be downloaded into a smartphone that doesn't, but this degrades the performance of the translation task. And finally, MPC, which is not ideal for floating point math and would require many rounds between client and server. So what we accomplished in last one day is we trained a sequence-to-sequence model on a dummy data set. We estimated the model parameters that will be required for this specific task. We implemented an encoding phase with the actual parameters, but random weights in the C library. And we estimated the performance and adjusted the parameters based on these implementations. So I'll give you a quick overview of the model architecture. We use a sequence-to-sequence architecture. This is the encoder phase where each of the INNs, the INN takes each word individually, maps it to the embedding, and then the whole encoder then outputs a feature representation for the entire phase. And the greens are the word embeddings that are often 250-dimension vector. Since the features are, since these all capture small features, we can actually take multiple phases together, and these phases are independent of each other, so we can pack together and send it to the server side, which can lead to better performance if we parallelize it. In the decoding side, the INN decoder takes the start character and then estimates the output of the model, takes the one-hot encoding representation of the final output, which then again gets input given as an input to the RNN. And we train this whole data set on these two data sets as discussed earlier. We estimated our parameters, and as you can see that the model decreases, the model loss decreases as the model number of parameters increases, and we showed that around 250 is a good estimate to achieving decent loss, yet it may not be the best, but it is good for a homomorphic encryption scenario. And these are a few of the examples of our translation task. As you can see that we translated from German to English. And the model performed almost, not accurate, but it was good. And now I'll give it to Sarah.
Sure. Okay, so through this implementation, we sort of got a chance to estimate how bad our communication costs were going to be, our runtime was going to be. So the good news is we're only sending one ciphertext from the client to the server, which is all of the boxes shown in the previous slide. And then the server, ultimately, the goal would be to do the decoding and then just send the result to the client, which is also one ciphertext. So we're only sending one ciphertext up and one ciphertext down. The downside is that ciphertext is about 900 kilobytes, but hey, it's not, the worst. Compare this to sending raw text, and it's definitely a pretty hefty overhead. The space cost in terms of what you need to store in order to be able to do this is dominated by these Galois keys, but that's fine. The runtime then, encoding takes about 6 minutes and 30 seconds for 8 layers. So that's for that 256 length vectors. Decoding is going to be about the same as encoding, plus a cost for doing something kind of like an argmax, which I will discuss briefly. We expect that the cost of doing this argmax step is going to be much higher than the rest of it, depending on which of a couple of different options we pick. So yeah, the model by itself runs in about 200 milliseconds. When we're doing it in homomorphic encryption, it goes up to minutes. But when we're talking about things like prescriptions, it takes pretty long to fill a prescription and to do a doctor's visit anyway. So 6 minutes, even an hour, is not ideal, but is fine if you're just trying to understand, what am I supposed to do with this medicine when I take it later. Okay. Okay, so I want to just really, really quickly walk you through some of the technical issues that we encountered in the process of doing this. So one was an issue about just how to do matrix multiplication using these ciphertexts that contain multiple vectors. Like how do we do a separate multiplication for each of these? The second one is the argmax issue, and the third one is also the argmax issue. The fourth issue then is just that machine translation is still not perfect, but that's probably not a problem that's going to be solved by SEAL. Okay, so what was hiding a little bit in the previous slide was doing these basically 250 by 500 matrix multiplications by a 500 vector, which is really two 250 vectors stacked on top of each other. But the point is that we have to do a separate matrix multiplication, matrix by vector multiplication on the different inputs at these different layers. And we had batched these vectors into one ciphertext. We know from Hao's great talk the other day that most of these good multiplication algorithms require rotation. But if you just naively rotate the ciphertext, you're going to run into this problem where you're not actually rotating each individual sort of logical unit within itself, you're rotating the entire ciphertext. So to get around this, we just write each vector in the ciphertext twice. We only need to cycle through it once, which means that once we cycle through the whole thing, the length of the vector times, we have now shifted the entire vector, sort of popped it off the end and rotated it around the side, and now we're able to go through this the way we want to. Okay. The second issue is this argmax issue, and I know I heard a couple other groups talking about this too. Can't really do argmax in homomorphic encryption, at least we didn't think of a way to do it. There are a few options. You could just do the default option of sending it back to the client. That's easy to do, but it really is not great for performance. You could do a linear sweep over your vector and just calculate the max n times using this new max algorithm, which, no, you're not over there, but using this new max algorithm that is apparently going to appear at AsiaCrypt. You could do this, you could switch the representation, so a couple of papers, including Chimera, will switch the representation into this TFHE, torus FHE, which is a lot better for doing nonlinear functions. But of course, this is not in Seal, and we didn't implement it in 24 hours. Or you could switch to a sort of an MPC representation. You could do the thing that Gazelle sort of tried to do, where you switch to MPC to do your nonlinear step. But that's probably worse than the TFHE solution. We tried replacing the argmax, but unfortunately that broke the model. I'm not going to get into why that's true. And anyway, you can't really do softmax that well in HE anyway. So we definitely found some interesting future research areas. One is like focusing on this argmax, how to do low-degree polynomial approximations for these things. Maybe we can try to figure out how to do that via machine learning itself, or maybe we can just use sort of traditional math in order to figure out how to do that. We may also have better luck with a different model architecture. This was sort of the most standard thing we could try. We tried it, and this is about how well it worked. So, thank you very much.
Any questions?
You claim that MPC is probably worse than HE because of floating point is not efficient in MPC, but I think some MPC experts in this room may not agree on that comment because there are some researches about efficient floating point arithmetic, and MPC is probably, yeah, as you mentioned, probably better in some argmax or some other functions. So, what do you think the main advantage of HE in this scenario compared to MPC?
So the two biggest things, I think, I guess I would be curious to hear about the floating point MPC because my knowledge of that was that it was still not very good compared to integers, at least. But the other thing is, if you're going to do sort of a standard MPC solution, then you're likely going to have a lot of rounds of communication between the client and the server, and this is one of the things that we want to avoid. If you do something secret sharing based, then you're definitely going to end up with that because you have to keep alternating between these additions and multiplications in order to do the multiplication. If you're doing a garbled circuit, then the client basically has to garble a circuit, send it up, and then have the server evaluate it. But if the client is capable of generating this, then we're sort of back to the question of maybe they could have just done this whole computation in the first place.
So two questions. So you didn't say much about your protocol design. Could you say a little bit more about that? So key distribution, like so who encrypts what to whom, under what keys, all of the kind of nuts and bolts of that?
So the good news is this is fairly simple. We're basically envisioning the a doctor's device as having this key. You could even do it per sort of clinic location. So as long as we trust doctors to not abuse this thing, we can have sort of, doctors have the keys required for encryption, decryption, and the evaluator just has whatever they need to evaluate. The evaluator being this cloud service provider sort of thing.
So the goal is to protect the confidentiality of the information from whom?
The goal is to protect, so the alternative to doing this would be to have we sort of mentioned them, to have either a cloud provider running this model sort of in the clear, so a Google Translate style thing, where the server gets the information, that the client being sort of either the doctor or the patient, whoever is sending this information. Using sort of the normal cloud-based model, they would just send that information via normal TLS or something up to the server. The server would then run the model in the clear as far as it could see, and then send the result back down. And it's that third server party, the compute party, that we don't want to have we don't want that party to be able to see this information, because the doctor and the patient both already have it.
So are you saying that there's two parties, a doctor and somebody else on the other end who have done a key exchange ahead of time and they share a key? Are you saying you're using public key or symmetric key? What's your description of your protocol?
We're envisioning, I think, let's say a group of doctors who are all using this service. And these doctors, for at least under the protocol that we described right now, are all sharing a key. This is sort of think of it as a single symmetric key for now. Probably the best way to do it would be if each individual device had a secret key on the device, and that all of those could be used, you could use each of those separately. But at least naively, we can't really think of a way to do that without duplicating this model a bunch of times. So. Thank you.